thesaurus, and in this video we're going to look at question 7 from the Step 1 Cambridge Maths paper from 2018. It looks like quite an accessible question. In a sense it's just algebra, but it is really a bit of a beast of algebra, and you've got to be super careful to make sure you don't make any mistakes along the way if you're going to be successful with this question. And there's a couple of subtleties towards the end as well. They're pretty tricky. So I hope this is going to be useful to you. Do like and subscribe if you do find it useful, and let me know in the comments if anything isn't clear. So part 1 really does tell us exactly what to do here. We've got an equation given and we've got to make this substitution. So I'm just going to replace x with pz plus q over z plus 1 throughout this equation, just splitting the cube into the cube at the top and the cube at the bottom there. But otherwise we're really just substituting in at the first step. So there's going to be a lot of algebra in this question, so we've got to try and do things as efficiently as possible and to keep track of all the terms and try to avoid making any silly mistakes. The first thing to do here clearly is to clear the denominators, so I'm going to multiply through by z plus 1 cubed throughout this equation, and we'll get 3pq pz plus q, so I'll have a z plus 1 squared term with this one, which actually let's multiply that out because we're going to need to do that. So let's write that as z squared plus 2z plus 1, and then we're going to have pq times p plus q, and we're going to have z plus 1 cubed here, and again we're going to need to multiply that out, so we get z cubed plus 3z squared plus 3z plus 1, just using a straightforward binomial expansion. So what I need to do now is to write this down in a way that collects together all of the z cubed terms, the z squared terms, etc. So I think I'll just do a bit more multiplication out first here. So this pz plus q cubed, again following the same structure here, it's good to be able to very quickly do a plus b cubed. So we'll do p cubed z cubed plus 3 p squared q times z squared plus 3 p q squared times z plus q cubed, and then for this next term here we're going to have 3pq times pz cubed plus 2pz squared plus pz plus qz squared plus 2qz plus q, and this last term here I'm just going to leave exactly as it is for now. And now I think I can see clearly enough where all the different terms are here, so I'm going to go through and collect all the z cubed terms together first. So I've got here a p cubed, and let me cross them out as I look at them. So, and then I've got, actually no, I won't cross them out because of the brackets, and then I've got another one here, so this is minus 3 p squared q, and from this final bracket here I'm going to have a plus pq times p plus q, so that's all the z cubed terms. Then for the z terms, so the z squared terms, we start with a 3 p squared q, and then in this second bracket here we've got a minus 6 p squared q, and I've also got a minus 3 pq squared from this term, and remember I'm going to multiply by the minus 3pq, and then we're going to get from the final term plus 3pq times p plus q, and that's z squared. It's important here to make sure we do check that these, we know from the answer that these z squared term here is going to be equal to 0, but it's very important for our working that we check that. And then for the z terms, we've got 3pq squared, and then I've got minus 3p squared q from this term, and I've also got this term here, which is minus 6pq squared, and from the final term a pq times p plus q times 3z, so let's put a 3 in front there, and then right, and then for the constant terms we've got a q cubed, and then this one here is minus 3pq squared, and then finally I've got a plus p plus q from this one here, and that's all going to be equal to 0. So now we're going to do even more rearrangement here. So we've got p cubed minus 3p squared q plus p squared q plus pq squared, just multiplying out the brackets there. And in the second lot of brackets here, okay, we've got 3p squared q minus 6p squared q, so that's minus 3p squared q minus 3pq squared, and then multiplying out here I get plus 3p squared q plus 3pq squared, and we can see in fact that this whole term then here is going to be equal to 0. So that z squared term does disappear in the way that we want it to. And similarly for the z term, I've got minus 3pq squared, just combining these two terms together, minus 3p squared q plus 3p squared q plus 3pq squared times z. So again, that term is going to be equal to 0. And then multiplying out the constant term here, plus q cubed minus 3pq squared plus p squared q plus pq squared equals 0. Now if we look at this, in the first term here you can see there's a factor of p in everything, so we should give this a go at some factorising. And I've also got minus 3p squared plus q plus p squared q, so that's actually just minus 2 p squared q, so with the p factor that's minus 2pq, and then I get plus q squared times z cubed. If I do the same factorisation over here, I get q times q squared, and again these two terms cancel to give this term with this one to give minus 2pq squared, and then factoring out a q, and then plus p squared, so that's equal to 0. And what you notice here is actually these two things that are factorised out are the same. So I've got p squared plus q squared minus 2pq, so I can divide both sides of the equation by that, and then we're just left with the very nice final answer, final equation here, which is just that p times z cubed plus q equals 0. So that is in the form that the question wanted, which was a z cubed plus b equals 0. So we've just found that actually a equals b and p equals q. So a lot of algebra there, but if you keep track of it all, we end up with a nice answer. And I think arguably if you don't get a pretty nice answer at the end of these a question like that, you know, possibly you've done something wrong along the way. So in the second part here, we need to show that this equation x cubed minus 3cx plus d can be written in this form: x cubed minus 3pqx plus pq times p plus q equals 0. So clearly you can see the structure of the equations is the same here. And we've got the condition that we need to have p and q distinct real numbers, and this condition that d squared is greater than 4c cubed is going to come out here. Now the structure here is clear, and you can see fairly quickly, I think, that we just need to make c equals p times q and d equals pq times p plus q. So the question is really, can we find p and q given a value of c and d? So I'll try and just solve these simultaneous equations to find formulae for P and Q in terms of C and D. So if we substitute this in here, then I get D equals C times P plus Q, and if we also write, say, P equals C over Q here, then I could put that in here and have D equals C times C over Q plus Q, and if we multiply this whole thing through by Q, we get dQ equals C squared plus CQ squared, which is a quadratic equation in Q. CQ squared minus DQ plus C squared equals 0. So applying the quadratic formula here, we get Q equals D plus or minus the square root of D squared minus 4 times C squared, so C cubed all over 2 times C. It's a bit confusing because usually we talk about A, B and C in the quadratic formula, and obviously we've got C in here as well, so I'm not using the usual letters from the quadratic formula here. Hopefully you can follow that, and you can start to see here where this condition that D squared is greater than 4C cubed is going to come out. Interestingly here, right, so okay, this is Q, we'll think about the condition in a second, but this is Q, and then obviously P equals C over Q, but because P and Q are perfectly symmetric in this problem, right, it's if I replace P and Q with one another here, nothing changes. Actually, really, this answer gives us both P and Q, right, so if Q is the plus 1 here, then P is the minus 1, and if Q is the minus 1, then P is the plus 1, right? But you could also write this as P equals C over Q, and then write that, so if I do divide by Q, it's like turning this fraction up and down and multiplying it, so I would get 2C squared over D plus or minus the square root of D squared minus 4C cubed, and actually it's not hard at all to show that actually this expression is equal to the same, that this is effectively equal to something like D minus plus the square root of D squared minus 4C cubed over 2C. All you've got to do is do your usual sort of rationalizing of the denominator here, and that will drop out. But that's just an extra bit of insight there. Okay, so it's sort of clear that this only works then when D squared is bigger than 4C cubed to make this discriminant positive, but to really be to get the marks here fully, you've got to make sure that you have that condition strictly D squared is bigger than 4C cubed, and it's a strict inequality, and that doesn't immediately come from the formula here unless you've noticed the thing I've just said about this being plus or minus, in which case you can say when this is 0, P and Q are both D over 2C. Perhaps you'll see that and say, okay, we need a strict inequality here so that we have distinct roots. You could do that. But another way is just to actually start with this condition directly and say, okay, D squared minus 4C cubed, what would that be equal to? Well, if I go back to my definitions here, that's going to be PQ squared times P plus Q squared minus 4 times PQ cubed. So if I factorize PQ squared here, I get P plus Q squared minus 4PQ, and multiplying this out, you would see that that's equal to PQ squared times P, well, okay, I can write it in full, P squared plus Q squared plus 2PQ minus 4PQ, which is PQ squared times P squared plus Q squared minus 2PQ, which is PQ all squared times P minus Q squared. Okay, and again we see here the condition is that that's bigger than 0, so when that's bigger than 0, it must be that P is not equal to Q, because if P was equal to Q, then P minus Q squared would be 0. So we can actually start with that condition and say, okay, in this case we can find P and Q that are not equal, and they're given by this formula, and they're exactly the ones that we want, and I think it's all super clear. So if you're finding this useful, please do like and subscribe and click the bell button to get notifications. Don't forget loads more content over on my website at mathsaurus.com and some useful and interesting stuff at the Amazon store, which I have linked below. So in part 3 we're asked to solve this particular cubic equation, x cubed plus 6x minus 2 equals 0. Now in the previous part of the question we've said that we can reduce something x cubed minus 3cx plus d equals 0 to this form from part 1 if we choose p and q by this formula, where I've just said, okay, let's use the plus or minus version and say, okay, p and q can be either way around here. Right, so you can match up the coefficients here and we can see clearly that c is minus 2 and then d is also minus 2. So that gives us, in this formula for p and q, that it's minus 2 plus or minus the square root of 4 and then minus 4 times minus 8, so plus 32, all divided by minus 4. So that's minus 2 plus or minus root 36, which is just 6, all over 4. And that gives us minus 8 over minus 4, which is 2, or 4 over minus 4, which is minus 1. And so these can be p and q either way around. So I go back to the equation in part 1, and I've got p z cubed plus q equals 0. And let's put this in as, so let's put p equals minus 1 and q equals 2, and then this gives us that z cubed equals 2, so z is the cube root of 2. Incidentally, if you did put them the other way around, you'll end up with a 1 over cube root of 2 here, but it won't end up changing the final answer. Actually, you can do some manipulation to check that if you want to, but I'm going to go this way around because the algebra is slightly neater. So I get z equals the cube root of 2 here, and then all I've got to do is, to get back to my solution for the original equation here, unpick that with my x transformation. So x is going to be p times z plus q, so that so hang on, which way around did I take it? I took p equals minus 1 and q equals 2, so I've got minus the cube root of 2 plus 2, all divided by the cube root of 2 plus 1, so I guess I should write that as something like 2 minus the cube root of 2 over maybe 1 plus the cube root of 2. Okay, and that's it, that's the solution. So the last part of this question just asks us to fill in the gaps about this case where d squared equals 4c cubed, and if we were paying attention earlier, we noticed that's exactly the case where p equals q, right? And if you take p equals q in the original equation, then this just becomes x cubed minus 3p squared x plus p squared times 2p, so that's plus 2p cubed. So the equation they're asking us to solve here is exactly this case where p equals q. The method of this question doesn't work for this case. If you think about the transformation in part 1, you just get x equals z plus 1 over, well, p times z plus 1 over z plus 1, so well, I suppose it's not totally useless, is it, actually, because so this is what I'm saying is this pz plus q over z plus 1 would just become pz plus p over z plus 1, so that's p z plus 1 over z plus 1, which is just p, right? And actually, in fact, what I was going to say without this is that one thing we can do is just notice that x equals p solves this equation, because we get p cubed minus 3p cubed plus 2p cubed, and that is 0. Okay, and perhaps if you don't spot that, you might also find that by playing around with this equation from part 1. Right? But anyway, the fact that x equals p solves this means that I can factor out x minus p from this expression using the factor theorem, and that factorizes then as x squared plus px minus 2p squared, and you should be able to do that fairly easily just by some matching up of the relevant coefficients here. And then we can factor this further as x plus 2p times x minus p equals 0. You could apply the quadratic formula to this again if you didn't spot this, but But anyway, either way we get x minus p squared times x plus 2p equals 0. So the roots here are x equals p or x equals minus 2p. Right? So we found the roots of the equation, and it says hence show how we can then solve this equation in the case when d squared equals 4c cubed. Right, so actually what do we have here? Well, if it's x cubed minus 3cx plus d equals 0, what we're doing is taking c equals p squared and d equals 2p cubed. So if I did d over c here, I just get 2p, and so actually p is equal to d over 2c, right? And actually they're the two roots that we have here, p and minus 2p, right? They're the roots. So the roots here would be either p, which is d over 2c, or we've got minus 2p, which is just then minus d over c, and then we're done. So I hope that was useful. A tougher question than it looked, this one, I think. Looks quite accessible with the algebra, but there's so much to do, and for step you've got to really be able to do it quickly and accurately if you're going to have any hope of getting a lot of these questions out in the time. Anyway, hope that was useful. Please do like and subscribe, and all of this paper is eventually going to be in a playlist. I've almost finished, so just a couple of questions left. Do let me know in the comments if there's anything else you're interested in, or if anything's not clear, and I'll see you in the next video.